ready to go. Remember to ask questions in the chat. I think Walter will give a 2-minute warning to the speakers. Is that right, Walter? Very good. So that hopefully we can keep a bit of time for questions as well. So without further ado, I will introduce the first speaker, who is Mathilde Cancet from Noveltis, who is going to be talking to us about improvements of the bathymetry and the regional tidal modeling in the Arctic Ocean. Over to you, Mathilde.
Thank you very much, Christine. Can you see my slides?
Yes, we can.
Great. So good afternoon, everyone. As Christine said, I'm going to present a kind of review of the work we've performed on the bathymetry and regional tidal modeling in the Arctic Ocean over the last years. And first, I'd like to acknowledge my co-authors from Noveltis and also from Lagos and from DTU Space, and people at CNES and ESA also for funding this work in the frame of different projects. There is a very tight link between the bathymetry and the tides, not only in the Arctic Ocean, but in general in regions where the tidal amplitudes are large. And the barotropic tides are very sensitive to the bathymetry features on the continental shelves. And today, the lack of accuracy of the current bathymetry datasets on the shelves and in the coastal regions, the major limiting factor to the improvement of the tidal models. So improving the bathymetry knowledge is really key to improve the ocean tide models. And shallow waters, the sensitivity of the tide models to the bathymetry errors can be used as a proxy to assess the bathymetry datasets. So this is the kind of work we have performed in different projects. First, in the CryoSat Plus for Oceans ESA project, which first aimed at developing, evaluating, and maximizing the measurement capabilities offered by the SAR and SARIN modes from the CryoSat 2 mission, but also which aimed at developing new or improved geophysical corrections, including a regional tidal model in the Arctic Ocean, on which we worked, and also trying to improve the bathymetry in the Arctic Ocean. So this is a work that we performed in collaboration with Ole Andersen at DTU Space. And more recently, we have worked in the frame of a CNES project to improve the bathymetry and the tides together in different regions of interest. So the Northeast Atlantic Ocean, the Mediterranean Sea, Australia, and also the Arctic Ocean. And on the bathymetry side, the idea was to collect existing datasets, either DEMs or mono and multi-beam soundings, and to match them into a reference bathymetry dataset, and to develop regional high-resolution tidal models with data assimilation on these regions. And in the end, we have 4 new bathymetry and tidal atlases in these regions. So in terms of hydrodynamic modeling, we used the TUGO barotropic model, which is developed at Lagos by Florent and which is run on unstructured grids with triangles. So we can have a different resolution along the coast. For example, in the Arctic Ocean, the resolution of the grid ranges between 4 and 7 kilometers along the coast, with sometimes higher resolution locally. And offshore, it ranges between 8 and 30 kilometers. And to validate the simulations, we use tide gauges and satellite altimetry data. And again, the idea is to evaluate the bathymetry through the model performance in terms of tidal simulations. So just to illustrate how the bathymetry impacts on the tidal solution, we have a ran the model on 3 different bathymetry datasets in the Arctic Ocean. So we had the LEGOS composite bathymetry and 2 versions of the air topo bathymetry dataset. You see here the maps of the M2 tidal component, so the main tidal component in the region, from each of the simulations, the model simulations based on each of these 3 bathymetry datasets. And the red dots show the vector differences between the model and the tide gauges. And we can see differences in the results. For example, south of Greenland, we clearly see an improvement from the air topo 1 bathymetry to the air topo 2 or to the LEGOS bathymetry, the reduction of the error at this tide gauge. And on the contrary, if we look at the Barents Sea here, we see a degradation when using the air topo 2 bathymetry dataset in the tidal simulation compared to the 2 other solutions. So there is a clear impact of the bathymetry on the tidal solutions. So in the Arctic Ocean, the Arctic Ocean is a very strategic region, as you all know, and it's very difficult to get access to accurate bathymetry data. And as it was already showed this morning by Ole in his very nice talk, it's possible to improve the bathymetry and first the gravity field using the CryoSat 2 data. First, because of its specific repeat period, which provides very dense spatial coverage, and also because of the high resolution, along track resolution brought by the SAR and ESA-ESRIN modes, and also because it's the mission that has the best coverage in terms of high latitudes, up to 88 degrees. So it's a unique data set to complete the sampling in the Arctic Ocean, and it improves, in fact, the bathymetry wavelengths from 20 kilometers to 100 kilometers offshore. On the shelves, the technique has more noise, and other approaches must be used. So this is what Ole already showed this morning. So the idea is that is to combine a prior bathymetry dataset with a gravity field based on CryoSat 2 to improve the scales in the bathymetry, because there is a direct relation between the gravity anomaly and the bathymetry. So this work was published by Adili Aboulaïtidjank in 2019, and you can have a look at his paper for more details. And so they consider the correlation between the topography and the gravity to do the inversion process, and they obtain predicted bathymetry here, which gives new information in the Arctic Ocean. And they have compared this new predicted bathymetry with the IPKO V3 bathymetry dataset in the Chukchi Sea, which is indicated in red here, and which in the IPKO V3 bathymetry is mainly constrained with all digitized depth controls or very sparse ship soundings. When they compare the new predicted bathymetry with this IPKO V3 dataset, and also with a cruise multi-beam survey from a cruise in 2016, they observe a general good agreement with the ship sounding between the predicted bathymetry and the ship sounding, and also they observe that the new bathymetry better resolves some specific patterns in the bathymetry compared to the IPKO V3 bathymetry. For example, with some deep valleys that are defaults, in fact, in the IPKO V3 bathymetry. But this only works offshore, and if we want to improve also the bathymetry close to the coast, we need to use other datasets. And we have integrated other datasets around Greenland in our basis bathymetry. So using the bed machine V3 dataset and also multi-beam soundings from the Oceans Melting Greenland project. And you can see here the difference in the relative difference between the merged datasets and the initial bathymetry datasets, with some differences of more than 50% in some locations, which corresponds sometimes to several hundred of meters. So it's a huge difference. And when running the tidal model on each of these bathymetry, we obtain different solutions. And you can see that when we compare our M2 tide solution with altimetry and tide gauge observations, with the initial bathymetry, we have strong errors at the tide gauge southwest of Greenland here. And this error is clearly reduced when using the new bathymetry, with a reduction of more than 30 centimeters in vector difference. So it's really a huge reduction of error simply by changing the bathymetry information again. So clearly there is a possibility to strongly improve the tidal simulations with a good bathymetry information. Another aspect which we have recently encountered is the coastline. In fact, we built the model mesh both on the bathymetry and on the coastline. And this is an example in the Frobisher Bay that we encountered. So we had a simulation on the low resolution mesh. It's a global model. And the error at the tide gauge, which is located in the bay here, was about 12 centimeters in amplitude. And when we used the high resolution mesh, the error strongly increased to more than 1.6 meters. So it's a really huge error. And just to say that at this tide gauge, the amplitude for M2 is about 3 meters. So that was a big degradation, and we can see that in fact what happens is that the tidal flow doesn't enter into the bay here, where there are a lot of small islands and very deep channels. And when we looked at the coastline, which is the GS-HHS NOAA coastline that we use here, we saw that, in fact, it is locally shifted by here about 500 meters. And it consequently changes, well, consequently the mesh doesn't fit with the ground truth in terms of coastline, and the path is strongly reduced, and the tidal flow cannot go through these channels. By simply changing the coastline manually, in fact, we can improve the tidal solution again and reduce the error by 1 meter. So that's just a manual correction, and of course we would need something more accurate. But just to say that this is a very important point, in fact, that we now encounter when we go to higher resolution. And of course, it's very important to say that we can only find this kind of problems if we have observations to validate the model. Just a few words also about the tidal modeling aspects that we have recently improved. We have added the Hudson Bay model extent. It was not included previously, and there are very strong connections in terms of tidal energy transfer between the Hudson Bay and the Canadian archipelago and the Baffin Bay. So it's important to have it in the regional model. And clearly, when adding this part in the model, we strongly improve the solution, especially on the diurnal waves. Then we have used the CryoSat 2 altimetry data to retrieve tidal constituents. I have to say that CryoSat brings again a unique spatial coverage over the Arctic Ocean, but it's also the only not sun-synchronous radar altimetry mission at these high latitudes. So it's the only way to have tidal components for all the components actually, or almost all the components. So it's extremely valuable for tidal estimates. And we have worked on how to grid this CryoSat data to retrieve tidal constituents, and especially looking at the way we interpolate the information to point in our grid. So generally, the point that is used is simply the cell center, but when we use the data centroid, we clearly obtain a much more consistent data set and also much more interesting points in the coastal regions. That's work we have recently done, and we have used this data to assimilate in our regional model. And these are the performance we obtain with our new Arctic assimilated model when we compare to altimetry and to tide gauges and with global models that are available in the region. So of course it's a bit biased in the comparison because part of the tide gauges are simulated, but in all models actually, so it's difficult to have a very independent data set. But clearly we see that there is a strong improvement of several centimeters on the various tidal components with this new solution, and also compared to the previous data set, the previous model that we have implemented, because especially because we added the Hudson Bay. So to conclude, on the bathymetry aspect, the CryoSat data are very variable to better resolve the Arctic bathymetry features offshore. And on the coastal and shelf regions, it's more complicated to use altimetry data, but other approaches are possible with satellite imagery or field campaigns. And we have shown that it can have a big impact on the tidal solutions. There is also a lack of external validation data for bathymetry, and that's why tidal modeling is very useful, as it can be used as an efficient tool to assess the bathymetry datasets on the shelves in particular. And thanks to the new release of bathymetry datasets, it's possible to continuously improve the tidal solutions. But we need also consistent coastline, as I showed before, if we want to go into high resolution modeling. We have improved our model by adding the Hudson Bay, as I showed, and CryoSat 2 is extremely valuable for the tidal estimates in the high latitudes, and to improve also the regional models. Of course, all this work can benefit to hydrodynamic modeling in general, not only the tides in the Arctic Ocean, and also it's a new correction for altimetry data, so it can be used to retrieve more accurate satellite altimetry information for the sea surface height and for the sea ice, for example. And all this work will also be used for the development of the new FES 2022 global tide atlas, which is currently developing. And just a word about a new project that we are starting just now in the Southern Ocean. It's a project funded by ESA in collaboration with DTU Space, with the Norwegian Polar Institute, and with UCL, where we will use CryoSat data to improve bathymetry and tide knowledge in the Southern Ocean. And I thank you for your attention.
Thank you very much, Mathilde. We'll take just one quick question, which is being asked by Pierre Prandy. He says, nice work, Mathilde. Is this regional model consistent with FES 14 at domain boundaries? How can we access regional tidal predictions?
So yes, the model is compatible with FES 2014, which was used at the boundaries. And also the grid, in fact, of the mesh is compatible with FES 2014. That means that we can patch directly to regional model into the unstructured grid of the FES 2014 model. That's a very important point that we try to maintain for all the regional models we develop. And for the moment, it's not available publicly, but it will be provided in different projects as altimetry corrections. And of course, we can discuss if you want to have some predictions of correction from this model.
Thank you very much, Mathilde. Thanks. So we are now going to move to the next speaker. Next speaker is Mathis Auger. I see you have switched on your video, which is good. Who's going to be talking to us about the Southern Ocean circulation under the ice from multi-altimeter combination. Over to you, Mathis.
Yes, can you hear me well?
Yes, can.
And my presentation is in full screen?
Yes, it is.
Perfect.
Perfect.
Hello everyone, my name is Mathis Auger. I'm a PhD student currently working at the L'Océan in Paris. And I'm going to present you my work, which is entitled New Insights into the Ice-Covered Southern Ocean Circulation from a Multi-Altimeter Combination. So this project was partly funded by CLS and partly funded by the CNES. And I've been working with Jean-Baptiste Salé at the L'Océan and Pierre Prandy at CLS. So for this presentation, I'm gonna present how we have built a new sea level anomaly product in the Southern Ocean, including its ice-covered parts. And I'm gonna also focus on the fact that using other satellites than CryoSat-2 allows to a better estimation of the sea level anomalies, because previously published products were computed only with CryoSat-2. So combining other satellites can really lead to improvements in terms of resolution and accuracy of the product. So a little bit of context first. I'm sure you're well aware of this, but still a little reminder. There's a huge issue of lack of observation in the Southern Ocean, and this is due to the winds, the waves, because there are very strong storms there. And of course, also due to the sea ice that can reach millions of kilometers squares seasonally. So as a result, we have maps like the ones on the right. So the top one is the number of ship data in the global ocean. And as you can see, it's pretty blank in the Southern Ocean. And the bottom right map is taken from the DUAX product, which is the reference for the global sea level anomalies in the global ocean. And what we can see is that there is a huge gap in the subpolar Southern Ocean due to the covering of sea ice. So to try to counter this issue, there have been lots of efforts in the last decades to understand how to retrieve sea level anomalies in the sea ice regions. So on the left, this is a SAR image, and the line, the colored line, is in the long track, backscattering power from a satellite altimeter. And what we can see is that we are able to detect from this parameter the leads in the sea ice regions. So this parameter, among others, allows to find the leads and to retrieve the sea level anomalies in these leads. So as a result, we have this kind of maps on the right, which are the number of lead data we can retrieve in a day from 3 satellite combinations, so CryoSat-2, AltiK, and CryoSat-2, and Sentinel-3A, Sentinel-3A and AltiK. So the map on the left shows the sea level anomaly along track with the sea ice here in white, and on the right, the figure shows the distribution in terms of different satellite altimeters. So that shows that we are able to retrieve a lot of measurements in the sea ice covered ocean, and that we can really make something pretty high resolution also in the ice covered parts of the ocean. Now, what is already done? So a little bit of context about what exists and what have been published. So as I mentioned before, there's the DUAX sea level anomaly product, which is a daily multi-mission product, but it has no data in the sea ice zone. And in 2018, there were two published products. So this one is from Tom Armitage, and there was another from Thiago Dotto, but the principle was very similar. It was using CryoSat 2 data to map the sea level anomaly monthly on a 50-kilometer grid. And it was a huge improvement because we were able to have data in the sea ice zone for the first time. So as you can see, in terms of comparison, so the direct comparison is not possible because it's not the same date. But just to see the idea is that the resolution is a little bit lower because we are using only CryoSat 2, and but we have data in the sea ice zone. And a little issue also that comes from the use of CryoSat 2 only is this kind of signal. I don't know if you can see my mouse here, but there are some stripes in the subpolar Southern Ocean, which are not physical but come from the orbit of CryoSat 2, and that are spurious signal that we don't want to have when we are building this kind of products. Now about what we have done. Okay. So we have done a new daily multi-mission Southern Ocean sea level anomaly product. So as I said, it is daily. It's on a 25-kilometer grid, and of course the objective was to reach the continuity between the sea ice zones and the open ocean. The time series spans 2013-2019, and we are combining CryoSat 2 measurements with LTK and Sentinel-3. So except from the use of other satellite altimeters, we also benefit from improvements in terms of processing techniques, with the first one being a neural network classification. So as we saw in some of the previous presentation this morning, the waveform that we retrieve from the open ocean, from the sea ice or from the leads have very different shapes. So here we classify all the waveforms using this neural network classification, and we only want to retrieve the first and second kind of waveforms, which so the first is the waveform we retrieve from the open ocean, and the second one is the peaky waveform we retrieve from the leads, so which is much more pickier and powerful because the leads are specular because they are protected from the wind by the neighboring ice. So we want to select both of these classes, and that's how we use this neural network classification. While before it was mostly done with empirical criteria. So now another major improvement, which is maybe a little bit more tricky to understand, is that we were able to compute the retracking with an adaptive physical retracker for LTK. So this retracker was able to continuously retract measurements from open ocean and the leads. So before, because of the difference in shapes between the lead measurements and the open ocean measurements, we had to use different algorithms, and this induced bias between the open ocean and the sea ice. So using this kind of physical retracker allowed to not have this kind of bias that is pretty difficult to correct, as I'm going to explain just after. So it's really a strong improvement to have, at least for one satellite altimeter, because it's only available for LTK, to have these continuous sea level anomalies between open ocean and sea ice. So we have this kind of bias between open ocean and sea ice measurements, but we also have bias between the different altimeter modes. So I think most of you are familiar with this map. It's the map of CryoSat 2 modes. So if we look at the Southern Ocean, we have regions with low resolution mode. We have regions in the sea ice with SAR mode, and we have regions closer to the coast with SAR in mode. So it means that each time we are changing mode, we have to compute a bias that is very difficult to correct. So for the previously published product with CryoSat 2, all of these corrections were done at the edges of the different regions we wanted to correct. So for example, if we wanted to correct a bias between open ocean region and sea ice regions, so we had to find pixels where there were both open ocean and sea ice echoes, so at the sea ice edge. And correct this and correct this bias only at the sea ice edge. Another way to do that was to do it along track. So if you're at the sea ice edge, you are going 25 kilometers to the open ocean, 25 kilometers to the sea ice covered regions, and you compute the bias at the between the two 25 kilometer zones. But the issue with this kind of method is that correcting a monthly bias at the sea ice edge can introduce unphysical sea level anomaly variability in the whole corrected regions. So that means that if we correct poorly this bias, it will introduce sea level anomaly offset on the whole region that is not physical at all. So that's why having a continuous surface for Alticay is really an improvement, because we have this continuous surface on the whole Southern Ocean, and then we can correct all of the other regions or altimeters by computing the bias on the full region we want to correct. So if we want to correct CryoSat 2 in the sea ice, we can just compare with Alticay in the sea ice and correct the bias. So this allows to compute the bias on a region that is much larger than before, and hopefully to have a really better accuracy on this correcting this offset. So now, after the processing and the mapping method is the same as DUAX-DT 2018, but with some parameters changing for the region. We have the kind of results on the right. So on the left, it's once again the map from Tom Armitage. So these are the same dates. So the left one is a monthly map, and the right one is a daily map. And the direct comparison shows a good agreement between both products, but yeah, an increase in resolution for our product. Now some hints of validation. The first thing to do was to validate in the open ocean. So that's what we have done by comparing with the DUAX product, which is the reference in the open ocean. And we found that 85% of total I3 grid points had a significant correlation with the DUAX product, greater than 0.8 over 2014-2018. And the remaining differences come from the fact that DUAX is using much more satellites, and also some different parameters that have been changing for our product of the mapping. Sorry. About the validation with in situ measurements, it's quite limited in the Southern Ocean because most of the tide gauges are either very landlocked or their time series is not concordant with ours. So it's very difficult to have a good comparison between our product and in situ measurements. But we have done it for a few months with a bottom pressure recorder in the Drake Passage. And you see, we can see a pretty good agreement on also in the ice covered periods of the bottom pressure recorder, which are in gray here. So this is encouraging. Another way also to validate is to compare directly the maps we can compute from individual altimeters. So we are mapping independently each altimeter and looking at the difference. So here we can see once again that the comparison visually is very good. So this is once again very encouraging. And the median standard deviation between daily maps in the sea ice region is 4 centimeters. Which is much lower than the range of values we can find in the region. And finally, to estimate the errors of the product, we have computed the product, but only using CryoSat 2 and Alticay, and leaving Sentinel-3A as an independent mission. And then we have compared long-track filtered Sentinel-3A measurements with the full product, but interpolated on Sentinel-3A tracks, and computing the root mean square error. So the root mean square error in the open ocean, the median root mean square error is 4 centimeters. It's 3.7 centimeters in the seasonally ice-covered ocean, and it's a little bit higher in the permanently ice-covered ocean with about 5.8 centimeters of error. So from this product, we have started to do a little bit of application about the physics we could see for the Southern Ocean from these results. So the first project is to look at the seasonal cycle of the subpolar Southern Ocean sea level anomalies and geostrophic circulation and its associated forcings. And the second project we're on is the eddy identification and tracking in the ice-covered Southern Ocean. So I will present just briefly what it's about. So first, to look at the seasonal cycle of the subpolar Southern Ocean sea level anomaly, a first thing to look at more generally was to integrate the sea level anomaly in different zones of the Southern Ocean. So we have delimited our subpolar Southern Ocean with an MDT contour of 1.8 meters. And inside the subpolar Southern Ocean, we have delimited two zones, so one onshore on the shelf and the other offshore. And we have integrated the sea level anomaly and compared with the forcings. So this is what it looks like. So on the top, it's the sea level anomaly integrated offshore. So here is the full time series, and here is the seasonal cycle. In blue, it's the sea level anomaly integrated, and in black, it's the wind stress curl. So we find here a very good correlation between the wind stress curl integrated over the offshore subpolar Southern Ocean and the sea level anomaly, which is pretty encouraging because physically this is how it works. A negative wind stress curl induces negative sea level anomalies. And for the onshore part, so by integrating only on the shelf, we found a very good correlation once again of the SLA of the sea level anomaly in blue, and with the zonal wind stress integrated on the shelf as well. So it's pretty encouraging to see that from our product we are able to link the variability and the seasonal variability with the forcings. To look a little bit about the geostrophic currents. So on the left, this is the mean zonal geostrophic circulation computed from Tom Armitage mean dynamic topography. So here in red, this is the Antarctic circumpolar current, and in blue, it's the Antarctic slope current that is flowing along the continental shelf of Antarctica. And on the right, these are the seasonal maps of anomaly of zonal geostrophic currents. So if we find, for example, here in blue along the coast, it's an acceleration of the Antarctic slope current. So we find this acceleration of the Antarctic slope current in winter and deceleration in summer. And there are plenty of other things that we can see, but I won't present it there. We have also done a decomposition to empirical orthogonal function, and we find a very promising results about linking all of this variability and the forcings. And to finish, so the second project we're working on, these are still preliminary results. So we are doing some eddy identification and tracking from the product. So this is a snapshot of some eddies we were able to track in the sea ice region. So it's pretty encouraging to see that we are able to track some eddies for several weeks. And we are still trying to do some statistical results and tests on these eddies. So for example, we tried to compute the eddy radius in function of the sea ice concentration and to look at the distribution of it. And we also tried to look at the ratio between cyclonic and anticyclonic eddies in the whole Southern Ocean. Okay, so finally, the combining CryoSat-2 with other satellite missions allows a strong improvement in spatial and temporal resolution. And it allows, maybe more importantly, a better correction of the bias between surfaces and altimeter modes. This is, I think, the most important improvement. We also started to look at large-scale variations of the subpolar sea level anomalies, and it shows a strong link with the wind stress seasonal cycle. And finally, we have also started to look at eddy tracking and identification, but we have to be aware that any error in the product will be understood as an eddy in the algorithms, in the tracking algorithms. So we have to be very careful on this, and we know it. So we are trying to, well, go forward slowly. And finally, maybe if I can add something, if you're interested in this kind of sea level anomaly product, but maybe more in the Arctic, I would advise you to look at the Pierre Prandy poster tonight. So it's presenting a product which has been done very similarly. in the Arctic. So thank you.
Thank you very much, Mathis. Again, we'll take one question and you'll have to answer the other ones online as you were. So the question by Jérôme Bouffard, who's asking, do you apply some multi-mission crossover minimization or collinear method before the OI procedure? And if so, which is the reference orbit mission?
No, we don't. I think I'm not sure about this. I think Pierre Prandieu would have a better answer for this, but I think this is because it would have been necessary to have the full tracks of all the satellites we use in the global ocean to correctly do this kind of correction. So we didn't do it. We tried to. We looked. We found that using the corrections that were applied by DUAX, so the orbit corrections applied by DUAX, were improving our results. So we used them, but we didn't do any specific study like this for our product.
Okay, thank you very much. If you could pick up the other questions offline, thank you very much.
Yeah.
All right. Okay, in which case we are moving to the next speaker. Next speaker is Stine Rose, who is going to be staying in polar oceans, and we're going to be looking at improved sea level from CryoSat 2 in the polar oceans. Very good, I can see your slides. Over to you. We can't hear you at the moment. You are muted. That's it.
Thank you. Great, so you can see my slides?
Yes.
Yes, perfect. Thank you for the introduction. First of all, I would like to thank my co-authors and also ESA for making this happen. So first of all, why are we actually studying the polar sea level? Of course, due to funding, but also as a scientist, when you look at this map of the global sea level, you see the white spots on the top and the bottom. And I know this is an old map from sea level CCI, but I don't think there's any current maps which actually covers the polar oceans. So why are they not covered? Well, it's because there's much more uncertainty to this region sea level studies. We have few tide gauges, we have few buoys, and also it was first with the CryoSat that we actually had a full coverage of the whole Arctic Ocean. We have the sea ice, which changes in season and has a permanent cover as well. When we study the polar oceans, we need to detect the leads in between the sea ice, and the satellite instruments are actually affected by the sea ice, and the range corrections are affected as well. So another issue is geophysical models, which are insufficient, especially the tide models and the dynamic atmospheric corrections are very have a high uncertainty. And then we have the retracking, where we are retracking both ocean and lead values. So I'm going to talk about an update to our Arctic sea level product from 91 to 2020. And we also have an Antarctic product from the CryoSat period only. It is a constant work in progress. Right now it's not available online, but if you contact me, you can get it. But it will probably soon be available online. Now it includes both the sea level anomaly and the dynamic ocean topography. And we only show results here from 95 due to the ERS1 quality. One big change to the product is that we use physical retrackers everywhere, which of course includes the sea state bias. We use the GPOT saboteur service from ESA, and here the sea state bias is actually not a number in Antarctica, where we have very high waves. So so that's an issue, but generally it improves the the sea level anomaly around the sea ice cover and the edge of the sea ice cover. Another improvement is the mean sea surface. We use now the DTU 15, and it will soon be reprocessed with the DTU 21. For the ALS data covering EIS2 and ENVISAT, this is done by Marcelo Passado. Here we have improved the sea level, the leak detection algorithms. So the issues we have is leak detection is sometimes we record false positives. For CryoSat in winter times, it's not a big issue, but in the earlier satellites, it's much worse. In summer, on the other hand, we have melt ponds, and we know that a satellite sometimes sees these as leads, and we get a much higher sea level anomaly in summer than we actually should. So we have started looking at the cryo to ice and the IceSat data to compare, and this will really improve the summer data in the Arctic Ocean. We also have an issue with the summer data, especially for the earlier satellites where we have large areas when missing data. So either you can interpolate data or leave it as it is, but we have a hole due to missing data. Then we have intersatellite biases. We don't talk too much about it, but it's actually, for example, for ENVISAT, we only have around a year of data. It is changing. The intersatellite bias is changing by seasons. And if you do it wrong, you can easily get a sea level trend that is way too high or too low. Then we have the transition, which we already heard in the other talk, from going from the ocean to the ice cover. Here is just a plot of a lot of empirical retrackers where you see how high the jump is. This is, of course, not a big an issue when you're using a physical retracker. And then again, we have the mode transitions, which also have to take into account. Just before showing the results, I have a little note on retrackers. So this plot shown here is a very messy, and I don't want to explain everything. But in the top here, we have a lot of empirical retrackers from the retired DTU retracker system LARS. And in the bottom here, we have GPOT from Salvatore. And it is plotted as a function of time, the standard deviation as a function of time. And as you see, GPOT improves, that has a much better standard deviation than all the other data sets. This is from Antarctica, and this is from Arctic. But we also see that the threshold 20% performs the second best. Looking at the median difference between the leads and the open ocean, we see that the threshold 70% actually minimizes the difference for Antarctic. And we see also that GPOT, it seems like it's it has a higher difference around wintertime, and this must be something we have to look into, but this could be due to a different post-processing of the data. The Arctic, the GPOT performs better, or the best. So here I just make a complete comparison of the grids from the old data set, the blue, and the orange in the new. And as you can see, the EIS2 and ENVISAT data has a much higher variability in the new data set, and we're happy about that. And the change in CryoSat is not as big in this average plot. So looking at the trend, we now get a trend of 2.6 millimeter per year. And I know it's dangerous, but looking at the trend, taking 5 years, taking 5 years away at a time, we see that around 2019 to 2019, there is a large jump in the trend. So something is happening, if you can trust the trend. Going more into the data, and looking at the Arctic Ocean annual and interannual variability, we have plotted the phase of the annual signal and the amplitude and the interannual variation. And as you can see with the phase, that it's actually has a high peak around late September, where we have a sea ice maximum, and in other parts of the Arctic Ocean, it's around November as expected. We also have what I think an issue in the Canadian archipelago, and also here in the Baffin Bay, there's a strange issue. The amplitude is pretty low in the interior of the Arctic, and we have some high values here in the Canadian sector. But more interesting, looking at the interannual variation, we can see that again, going to the Arctic sector, we have these small high values, and so it's changing interannually around the large river outlets, and I will tell you more about that later. We also calculated the geostrophic circulation. This is done from the dynamic ocean topography, and on the right, on the left, we see the background DOT, and on top the geostrophic circulation. And you can see the pattern that it's going around the Beaufort Gyre and out the Frame Strait, and yeah, the circulation pattern is as expected. Taking the CryoSat period, the anomaly from the CryoSat period with respect to the total time series from 95 to 21, we get the map over here, and I have a plotting issue around the rim, but otherwise we see that there's a strengthening of the Beaufort Gyre, and we also have a strengthening here in the the Laptev Sea, where we have a much stronger current, and we also see a negative current speed of the Frame Strait, and I'm not sure. I have an issue with the earlier data right now, so I'm not sure I will trust this currently, but this is what I see. We've done the same for the Antarctic data set, and here we also get all the large circulation patterns. We have the Ross Sea Gyre, we have the Weddell Gyre, we have the polar current, and the Antarctic front. So the data picks up all the large circulation patterns. So looking more closely into the Beaufort Gyre, we have defined the Beaufort Gyre extent similar to Reagan et al. In 2019, where they take the closest contour of the DOT around the maximum Beaufort Gyre value and define the gyre from this. So we see the dynamic ocean topography is rising in like this stepwise pattern, and we also see the same from the area and the volume of the data. The area and volume have these drops on the way, and I'm not sure this is an issue with the contours or if it's actually a physical signal. Here we can also see a closer look into the annual variation, and with the low in May and the maximum in November. Going back to the Russian shelf, it has historically been a very difficult area for altimetry. It is we have very little in situ observations, and this is an area where the sea ice grows a lot, and we have sea ice coming and going. So it's been an area where oceanographers are using models instead of satellite observations. But my say is that you could actually, with CryoSat, you could start using the observations instead of the models, because it really performs very well in this area. Here I've just given an example of a tide gauge. We have a very nice seasonal, it cuts the seasonal patterns very good, the seasonal signal, but the trend is not really captured. And I must say that the sea level anomaly has not been corrected for GIA, And we also have a lot of issues with these tide gauges, that there could be some depletion or other things that we don't know about. On the top figure here, we see that the interannual variability of the sea level anomaly, and we see that the interannual variability has some high values just around where we have an outflow from the large river systems. Looking at the Orb and Kara Sea, we see on top the sea level anomaly, then we have the discharge in square kilometers, then we have the manometric sea level rise, or sea level, and then the salinity in PSU, and the temperature in degrees Celsius, and the Arctic acceleration index. So we have not calculated the temperature and salinity into sea level equivalents because of too large uncertainties in the density. We need to integrate density down the ocean's surface and down, and it's just too uncertain to include. So here you can just see is it rising or falling. But you see that there's this small sea level rise in the area around Orb, and the same we also see from the tide gauge, not the tide gauge, the river gauge, the discharge data, and it's clearly a manometric signal, but it doesn't show all it cannot explain everything, and here I guess it's maybe due to some salinity temperature changes as well. But yeah. So in summary, we have a new improved product with both sea level anomaly and dynamic ocean topography. It is available soon, or else you can just write me an email and I can give you the data sets. We have improved the ERS2 and ENVISAT data, and we also use the physical retracking on all surfaces using Samosa Plus for CryoSat 2. We have included a better mean sea surface, and I want to say that CryoSat have improved the possibility of studying oceanography in the polar oceans. There's still a lot of things to do, and indeed we're missing validation data sets, as we just heard as well. And then in the end, I just want to say that you have to look out for cryotemporal products, which is very simple thematic products coming out of from ESA soon. So thank you for listening, and thank you for providing the data.
Thank you very much, Stine. I can't, oh no, I was going to say I can't see any questions, but that's not true. There's a question by Felix Müller. Thank you for a very nice presentation. In case of the monthly DOT grids, which gravity field, bracket geoid, did you use here? Thank you very much.
Yes, so I've derived it from the MDT, so it's in this data set I've used DTU 15 mean sea surface, and then you need to use MDT that has the same mean sea surface. So that's the DTU 13 mean dynamic topography, and the DTU 13 is made from Ogmok geoid. So it's the Ogmok geoid. A long answer for that.
Okay, thank you. All right, thank you very much, Stine. Let's move to the next speaker. Next speaker is, I shouldn't really introduce him because he's from North, but I'll do anyway. Is Chris Banks, who is doing his Godfather impression again by having the light all in the wrong place. Chris Banks is going to be talking to us about the evaluation and scientific exploitation of CryoSat 2 ocean products for oceanographic studies. Over to you, Chris.
Okay, thanks, Christine. It's my camera. I blame my camera why you can't see me. Hopefully I am actually on full screen as well, yes?
Yes, you are.
Yes, okay, that's great. So moving away from the polar oceans now, the The title is Evaluation and Scientific Exploitation of CryoSat-2 Ocean Products for Oceanographic Studies. So I want to acknowledge my collaborators at NOC, and also thanks to the people listed there who've contributed at different stages of this particular work. So to give an overview, I'm going to sort of give an overview of what we do at NOC on looking at the ocean products. So it's kind of split into two parts. The first part will be very short, and it's how we provide routine reports on the CryoSat ocean processor, so the COP, looking at such things as data latency, the quality of the geophysical sea surface height, significant wave height and wind speed, and also validation or comparison against other data sets such as in situ measurements, models, other satellites, which is currently JSON-3, and also looking at the global mean sea level time series. And most of the talk I'm going to look at specific detailed scientific case studies, mostly to do with sea level anomaly. So just to point out that there are daily and monthly reports available on the CryoSat Ocean processor. So these are available at 3 time steps: the near real time NOP, the intermediate ocean products IOP, and then the geophysical ocean product, which is has the best orbit information. The daily reports are sitting there and the link for the website there is if you search for CryoSat. The most up-to-date one on there at the moment is the data from Sunday. The monthly reports are not available at the moment as we're in between contracts with ESA, but we hope to have those being made available over the summer. As kind of a quick example of the kind of material found in those reports, we've got the NOP on the left, the IOP on the right, and this is our plot of significant wave height from those two products in the top plot, and then the distribution in the bottom plot with the satellite in LRM, SAR mode, and also pseudo LRM. And we see straight away in that particular plot that we notice that there are some passes from the NOP that are not there that we see in the IOP. So we can see, you know, that's the sort of thing that we're picking out in the daily reports. So the rest of the talk, I want to look at specific examples. This is just a single slide of some preliminary results of looking at a tsunami that struck the Indonesian city of Palu, which is vaguely situated underneath this black diamond here. And it was actually Walter who initially pointed out that he thought he could see some signals of this tsunami in CryoSat data. So we've got a track here in pink of CryoSat. We've got a red diamond, which is just a particular point in time. And then on the right-hand side, we have got at the top, the sea surface height anomaly, the sigma naught backscatter, and the significant wave height. And we see that that red line there is the red triangle on the left-hand side. And we get some very unusual results. And I am not suggesting that we were seeing sea surface height anomalies or significant wave heights of these values here. It's because at that point, the waveforms were very un-Brown-like. So the model was actually retrieving something that really wasn't represented with this particularly kind of jumbled sea surface at the time. It's also worth pointing out that that marked point there, the red triangle, CryoSat went over that 2.4 hours after the earthquake, which was only about 500 kilometers away. So we're not actually looking at the initial tsunami signal. We're looking at some kind of reflection or refraction within that sort of semi-enclosed basin. So the rest of the talk, I'm going to look at work that we've been doing on a NOC sea level anomaly product, which is a level 3 product. And it's just to prove the utility of CryoSat. You know, I'm very aware that there are other products, multi-satellite products, that are available. So CryoSat's orbits cover the oceans. The idea is to develop this daily quarter-degree product using the Geophysical Ocean product. So that's the one with the best orbits. It's the baseline C, which is the most recent processing baseline for the ocean processor, and it's quality controlled data only. So we're looking at spatial temporal averaging of the 1 Hertz data from January 2011 to October 2020, and that what we end up with is data from the 24th of January to the 8th of October, and between 60 north and 60 south, and it's in LRM and SAR modes. So it's an animation, which I'm not going to put on the whole thing, but you see that you get sort of a lot of westward propagating features in the more dynamic regions, such as Gulf Stream, North Atlantic Drift, and the Cresceo. We get some potentially very ungeophysical results again, and this is, we've seen this in other presentations. This is linked to the unique orbit of CryoSat. And again, around the Southern Ocean, we're seeing some features that we're not sure are actually real. If you look over here, you also see some trackiness, where you see, you know, the path of the satellite quite clearly. But in general, you know, we think that's quite good from a single satellite. Hopefully, we'll move on to the next slide. Okay, so in order to check whether this is working, we did some validation. So we're just comparing with JSON3. So on any particular day, any JSON3 data within that particular grid cell, we took the average of that and compared it with our sea level anomaly product. So we've identified a number of study regions which are marked on the left hand side, and then what you've got here is a series of 2D histograms with the JSON3 on the y-axis and our NOC sea level product on the x-axis. And what we see is, so the color scale runs from yellow to blue and is the intensity of the number of observations. So most data points sit on the pink 1-to-1 lines, and then we have 2 regression lines, the detail of which are not really important at this particular point. One minimizes the uncertainty in predicting from JSON3, and the other from predicting from our product. But we see that, you know, we do have some scatter, but generally the results are very encouraging. We can also look at global mean sea level. So what we've got here in the lower panel is we've got from 2011 into 2020. On the y-axis, we've got the global mean sea level in millimeters, and the thick black line is our product. So we see that you know, we see the sort of the general slight upward trend in sea level. I've also plotted on here a number of other products. So Colorado and Beckley, they are both based on JSON series of satellites. And then at the top, we've got from data from a VSO, and then the red line is the CCI. So the ESA Climate Change Initiative data, which finished in 2015, which is marked by this dashed line here. And what we see is that in general, there's very good agreement. One thing that we kind of were a bit concerned about was this double peak either side of New Year 2014, which there's no evidence of that in either the CCI or the AVISO. There is a slight evidence of it within the 2 JSON products. And when we looked at the multivariate ENSO index, which is the top plot, we see that either side of New Year 2014, we do see peaks in the ENSO index. So we wonder if actually the CryoSat product is able to measure that. We also look at regional sea level trends. So the top plot shows regional sea level trends from our product for the full time period of which we have data. The hatching, which is not particularly clear on screens, I don't suppose, shows where that is significant. But I mean, that's a relatively short timescale. And then the two bottom plots are to show how our product agrees with the ESA Climate Change Initiative product over a much shorter time scale. But you see that the general pattern and the magnitude of those trends are very similar. So I should say, you know, CCI does contain CryoSat data, but it's not just CryoSat data. So there is a measure of not necessarily independent data. We can also look at a bit more at those ENSO signals. So we have this region here to the northeast of Indonesia, and from -5 degrees to 10 degrees north. And if we, so what we've got here in the middle plot here, this is a Hofmüller or time longitude plot. So we've got longitude along the x-axis, we've got time along the y-axis indicated on the far side here. And we will calculate for each degree of longitude or each quarter degree of longitude, the average over that box of sea level anomaly. So we see this very major sort of negative sea level anomaly here in about 2016. And if we compare that with the left panel, which is the ENSO index, we see this large positive ENSO event. And again, we see similar events in more recent years here, where we have this sort of less obvious ENSO event, but we still get the negative sea level anomalies in the west. We can then also have a look at Rossby waves or large nonlinear eddies in the southern Indian Ocean. So that's this box here, which has been used before to look at Rossby waves in altimetry and other products. And again, we'll use this kind of concept of time longitude plot. So here we have longitude along the x-axis, time on the y-axis. On the left-hand side, that is from the CCI. So you see that it's over a much longer time scale. And then our product on the right-hand side over a shorter time period, but coming more up to date. This is at 25 degrees south. Both of these plots, there is some filtering of westward features in there. And if we've used the radon transform to calculate that angle that minimizes, you know, that works for that whole image, either on the left or the right, to calculate the speed. And what I find very satisfying is the fact that they both actually come out with the predicted, or a speed of 5.9 centimeters per second. And if we calculate that for all possible latitudes, so we now have latitude on the x-axis running from -15 on the right to -13 on the left, and speed on the y-axis. With our product in the black line, we see a series of estimated speeds. The CCI in red, which again, this is operating over a different time period. We're not, you know, there is some overlap, but there is different time periods, and we see that some of those speeds calculated are incredibly close, if not identical, to those that we identify in our product. Just as from a previous study where we used SMOS to look at Rossby waves, so that's the estimate of speeds in the blue dashed line from salinity in SMOS, and then from temperature in the SMOS product. We see that, you know, we're still looking at a similar product. The grey lines represent the first three modes of baroclinic Rossby wave predictions from World Ocean Atlas. And again, you know, I can see that Paolo's getting very excited in the audience there. But I think it's a really nice demonstration of how CryoSat and CCI are in agreement. So in summary, there are no major ongoing issues with either the NOP or the IOP. The GOP will be analysed and hopefully monthly reports produced over the summer. So we've now got 11 years of CryoSat data from the beginning of the mission with a single processor, which is baseline C. They're suitable to be used as an independent look at ocean processes. The orbit of CryoSat complements the kind of more traditional altimetry record from repeat orbit missions, and we've shown the scientific validity and utility of CryoSat sea level ocean products through these case studies, and we hope to make this product available shortly. And just to conclude, I think to continue what Walter said earlier about the camel's nose entering the tent, I hope this has shown that the camel has not only entered the tent, made itself at home, but it's now also invited its family to stay. So thank you.
Thank you very much, Chris. Yeah, I'm one of the camels as well, I'm afraid. But anyway, there is time for questions. So there is one from Walter. Walter, do you want me to read it, or do you want to read it yourself?
Well, I guess I can do that. Thanks, Christina. Chris, I wanted to thank you for this. And indeed, the camel is quite far in the tent, and I think it's a wonderful thing. I'm particularly pleased to see so much ocean dynamics being looked at with a long repeat orbit, because way back in the ERS-1 phases E and F, long repeat orbit of 168 days, Remco and I were showing that you could recover some mesoscale oceanography from that. And at the time, of course, the ocean community was certain it wanted short repeat time, exact repeat orbits. But anyway, I wanted to ask, I was looking at your plot of the global mean sea level that you have determined, and it looked to me like there might actually be an apparent slight deceleration of, or a slowing down of sea level rise over the period you were looking at. But I think over the period of the entire altimeter record, it seems to be an increase in rise. I didn't know if your time period is long enough, and if you wanted to comment on sea level acceleration, and then also if you might say anything more about what you think is going on in that apparent tsunami observation. What is actually happening to the sea surface? Is it stretching or shrinking or something? Surface tension? What's going on? What is the altimeter really feeling in that tsunami, if you would speculate about that? Thanks.
I'll answer the tsunami question first, and that is, I really don't know. So I'm on my second tsunami modeler trying to get some model results of what is actually happening. You know, are we actually seeing the result of a tsunami, or are we just seeing, you know, some other feature that we're not able to take account of? But I don't know. I have no idea of what the surface of the ocean looks like after a tsunami. I can, you know, on the scale that an altimeter would see. If anyone has any ideas on that, then I'll very much welcome their views and their knowledge. As to the global mean sea level, I think the time periods are too short to say anything, you know, really major about whether there's a slowdown. So I have, you know, I can show one other slide, if I can find it, which shows, because I thought somebody might ask a question about. So they're the actual trends that we've identified from the various products. You know, so this is over the full period, the trends, and this is over the earlier period. So, you know, based on what you said, you know, in the earlier period, we were seeing 6.1 millimeters per year, and we're now seeing just over 4. So there is some evidence, but I wouldn't want to draw too many conclusions from that at this stage.
Thank you very much, Chris.
Okay.
We're going to move on to the last talk in this session. where we are going back to the Arctic with Camille Lick, who's going to be talking to us about characterizing the extent, shape, and location of the Beaufort Gyre in the Canadian basin of the Arctic Ocean using satellite data between 2003 and 2014. So over to you, Camille. We can see your slides.
Okay.
And we can hear you, so go ahead.
Okay, I should apologize for the long title, but that's just the title of the paper. Sorry for that.
It's the abstract.
Yeah, everything's there. Basically, you get the summary and so on. And I should also probably apologize because this is basically a paper that we published at the end of 2019. So it's a bit out of date, and a lot has been done recently. But I think it's still worth a shot. I should say up front that was work that was led by ESA-ESRIN, who was my postdoc at that time at Ifremer in Brest. And the second thing I should apologize for is I am not an expert in any satellite data producing or anything like that. So basically, the whole study is based on the data set that was at that time produced by Tom Armitage, who was at JPL at that time. And I'm going to talk way less about the data and the product itself, and I'm going to try to show you some example of what we think we can do with this kind of data set and what they're extremely useful, and they are full of information when you care about ocean dynamics. Okay, I need to, okay. I'm going to start with quickly some background, explaining what we were trying to do and why we start looking at the data sets initially. So no one will be surprised when I say that the Arctic basin is the main reservoir of oceanic freshwater. You have a lot of freshwater stored in the Arctic in form of both sea ice and liquid. And what I'm showing there on this map is an integrated freshwater content. So basically, you integrate an anomaly of salinity up to a certain depth. And you see that there is a lot of freshwater stored in the Arctic basin, and most of it is stored here in this red bulb. And that actually corresponds to the Beaufort Gyre and the dynamical feature that my talk will focus on. And the reason we cared about the viability and the storage in the Beaufort Gyre is twofold. First, we know that the gyre has been accumulated a lot of fresh water. And that's what the figure shows here. That's from a paper by Andrei Pushtinsky, where from mooring observation, CTD cast, ITP, so basically the equivalent of Argo data in the Arctic, you can reconstruct the evolution of freshwater content in roughly this box. And you see that from 2003 to 2014, so the timescale I'm caring about, you accumulate a lot of fresh water. You nearly double up the amount of fresh water that you stored in the gyre. And okay, you could just say there is more fresh water there, but why do we care about that? We care because we know that there is a link between the variability of the fresh water stored in the gyre and the export from the Arctic to the North Atlantic. So this figure is a circulation. So basically you get a gyre there, and when the gyre releases this fresh water, when the gyre spins down, you can release the fresh water and export this fresh water to the North Atlantic. And this has been really nicely shown by Alexian and Marika Holland in 2013. So they use a model, and they look at the model under different IPCC scenario, from the least extreme to the most extreme in red. And she shows these nice different events. So basically, when you start increasing the CO2 from the not that much to a lot in red, you start melting all the sea ice in the Arctic, but you also accumulate more fresh water coming from the precipitation, the river runoff, and so on. And as a result, you will start exporting more liquid fresh water through Fram Strait. And by doing that, you will decrease strongly the sea surface salinity in the Labrador Sea here, but that's also true in the Nordic seas. And when you start decreasing the sea surface salinity, you basically shut down any convection that happened there, and then you will slow down the AMOC. So these kind of events have been shown as a projection in the future, but basically that's the rationale for caring and wanting to monitor the variability of the freshwater content in the Beaufort Gyre. The last piece of rationale I want to give you is this slide and the next one, and basically I just want to explain what we know of the Beaufort Gyre and how that's functioning, and what we knew before we starting this study. So basically, when you look at, you get the Beaufort Gyre here in the Canadian Basin. I'm sorry, I'm shifting and changing projection every plot, so not easy to follow. Sorry for that. But you get Greenland here and Alaska and Canada here. And when you look at the mean atmospheric circulation in the form of the mean SLP, you get this strong structure here that we call the Beaufort Sea High, and that basically corresponds on average to the Beaufort Gyre. So you get a feature in the atmospheric circulation that mirror and follows the Beaufort Gyre on average. Of course, the problem in the Arctic is it's more tricky than just wind forcing. You get sea ice, and when you have sea ice, the forcing is very different. The amount of momentum you actually input to the ocean is strongly modulated by the presence of sea ice. That was shown from a model study by Michel Samados, by Torge Martin, and so on. And this actually illustrates really nicely what's going on. Basically, if you think of the Ekman pumping, so that's the curl of the stress at the surface, and you only compute it from the wind here, so North America here, and you get this picture that's produce a strong downwelling in blue. So that's, if there were no sea ice, that's the forcing you would get. But because you have sea ice, the ice is actually the fact that the ice is drifting exerts another source of stress when you start computing the Ekman pumping. And if you only consider the wind and the ice, then you get even a stronger downwelling, that pattern with very large value of Ekman pumping. But actually, if you want to do a fair computation, you should take into account the surface current as well. So basically, as the ice drift and the surface current are basically of the same order of magnitude, you actually need to take both into account to compute the downwelling properly. And that's what is known on this last figure. And when you actually take into account UG, so the geostrophic velocity estimated from satellite observation from the product by Tom Armitage that I'm going to present just after, the forcing is strongly reduced. And you even have upwelling some year and downwelling in other year, but a large time and space variability that you can only know if you get a knowledge of the surface current, ocean surface current. So, okay, forcing. And then what's going on in the gyre? It has been, before we started that study, basically it was only done mostly from very simple process model and theory, including some of my past work as a postdoc. And basically the balance we have in mind for the Beaufort Gyre is that you force at the surface, this Ekman pumping that I was just showing before, and then you're not going to, you tilt your isopic null, it starts to deepen, but they're not going to deepen forever. So you need something to balance out the input of momentum. And what's going on is you start generating baroclinic instability, and you start generating eddies, and that's basically balancing out the input at the surface. So that's the balance we had in mind. We know that the time scale on which that balance occurs is more than a decade. So the gyre will have a memory of the forcing from a decade ago. So that's basically where we start from when we started this analysis with ESA. And I'm going to show that this idea that the gyre is in isolation from the world around here is actually quite flawed when you start looking at the data properly. So, okay, what we did in these papers is we tried to characterize the time and space variability of the gyre. That could have been my short title, but it would have been too easy. And we tried to look at the role of the forcing and the role of the bathymetry to explain the variability of the gyre. And as I was saying, the full analysis is based on the dataset produced by Tom Armitage, which is based on Envisat and CryoSat. So I'm just going one map for an average in 2003. When we start with CryoSat, it's actually much nicer because the North Pole gap is actually much smaller, so you can actually get the full gyre, describe the full gyre, which wasn't the case at the end of the period when we only have AVISAT. So we have a product that is monthly, cover a bit more than a decade, and the resolution is 25 by 0.25 times 0.75 degrees. And we also use sea ice concentration and wind, SLP and wind from ERA Interim. Okay, I just want to make a short aside to tell you why, by looking at sea level anomaly or DOT, we can actually estimate freshwater content. And that's basically, we are in the Arctic, so we are in a cold environment, meaning that the density is solely determined by salinity. So you're basically your static height, which is the difference between DOT and the ocean bottom pressure, is basically giving you an indication of freshwater content. So basically, we should make the analysis with these two terms, and the ocean bottom pressure can be estimated from GRACE. It works actually fairly well in the Arctic. But there were this nice paper by Catherine Gareth, and she showed when having a first attempt at looking at the variation of the freshwater content, that if you reconstruct solely from SLA or DOT, or if you add some information from GRACE, so that's basically the dot versus the cross here, you get the same estimate. So basically adding GRACE doesn't do much to improve the evaluation of freshwater content. So in the remaining of my talk, I'll talk about DOT as basically a proxy for static height and a proxy for freshwater content. Okay, so the first thing we did was just to describe the gyre. And to do that, the definition we took was to take the maximum DOT in a square region representative of the Canadian Basin, and then we compute the largest closed contour around that center. And we do that for each month, which is the resolution of the product. And you see that basically you can compute a mean seasonal cycle over the full period. And you see that the gyre between summer and winter will tend to expand and reduce again. It's basically expanding in winter, shrinking in summer. But when you turn to the internal variability, the variations are actually much larger. And when I do the annual mean of my gyre, so one contour, one color is 1 year, you see that the gyre is actually, over the period from 2003 to 2014, the gyre is actually expanding a lot, growing. And it's also, the center is actually shifting northwestward by a lot. I mean, from blue to red, you have shifted the center of the gyre by a lot over the time period considered. And the background here is actually the bathymetry, and you get shallow bathymetry on this side. And I'm going to talk more about that. But actually, it is quite interesting that the gyre is able to expand over very shallow bathymetry here, and here are some consequences for the freshwater content and the dynamic of the gyre. Okay, so the second thing we did is you can actually estimate the intensity of the gyre, which is well represented by the maximum DOT at the center, and you can also compute the gyre area. And one thing we were kind of surprised by is that the two proxies are actually not correlated. The maximum, so the intensity, is actually increasing up to 2007, 2008, and then basically plateau. While the gyre area tends to increase, you have somewhat of a linear trend over the full time period. And it's quite counterintuitive, because I mean, in the literature before, people were talking about the gyre spinning up, and gyre spinning up is both expanding and increasing in intensity. But the two things are actually two different, give you actually two different pictures that we think is related to different forcing and different behavior of the gyre. Okay, so we try to understand what the atmospheric was doing and how it was responsible for that. So we step away from all the complication of you have sea ice, the downwelling is actually not the wind and so on. But we start by looking at the wind just because that will give you at least where the main forcing is positioned in the basin. So what I'm showing there is the mean sea level pressure for each year, 2003 to 2014. And in black, you get the gyre for this year. And the circle in black is the center of the gyre. And the second thing I want you to note is the white diamonds, which actually indicate the maximum SLP. So what would be the center of the Beaufort Sea high, the atmospheric forcing. And you see that there is large variation on the intensity of SLP. For instance, if you look at this year, 2008, 9, 10, you will get fairly strong forcing over the Canadian basin, and at the response, the gyre will tend to expand quite a lot. But the position of the Beaufort Sea high change a lot as well. It's which one? This one, for instance, to 2012, it's completely not aligned with the gyre. So you can have a strong forcing, but totally not efficient actually at forcing your gyre directly. So what we're showing there is that it's not just the intensity of the forcing and its variability that matters, it's also the position of the forcing that matters. The second thing we wanted to look at is the interaction with bathymetry. And to do that, what I'm showing there is the gradient of the DOT, and the gyre is in purple on top of it for, again, each year. And you see that there is a strong asymmetry between what's going on the southern side of the gyre and what's going on the northern side. And you see that it gets much steeper on that side because basically that's switching bathymetry. So you get the gyre that is getting close to bathymetry and it cannot expand anymore, so it starts steepening. And by steepening, it's spinning up largely and you increase a lot your geostrophic velocity. On the other side, it's not really constrained by bathymetry and the gyre can expand and expand forever without reaching a limit and without spinning up largely. And another way to look at that is by doing this Hofmüller plot. So I'm basically looking at the DOT along the gradient of the DOT along the 74 degree north. So that's this line here. And so you start here on that side and then you go on the other side over the Chukchi Plateau. And we see exactly what I was explaining. Basically, the gyre starts to be quite low and not with a very strong intensity at the beginning. And then it reaches the bathymetry, it reaches the plateau, it starts steepening, and then it bridges over. And you get the yellow-purple that actually bridge over the Chukchi Plateau and will expand over it. So you really have this strong interaction that you can start investigating and know what's going on with the altimetry. I think I can skip that and I'll finish with my conclusion. As I was saying, the Arctic freshwater is mostly stored in the Beaufort gyre, and this amount of freshwater has largely increased over the past 20 years. From satellite observation, we found that the Beaufort gyre has increased in size, intensified after 2008. These two are not correlated parameters. And the center has shifted a lot northwest. And when we talk of the spin-up of the gyre, it's actually these three components that describe what the gyre spin-up is. We found that the intensity is mostly sensitive to the strength of the forcing, while the gyre area is also sensitive to the location of the Beaufort Sea high. And then we try to investigate a bit further the shallow bathymetry, the role of the shallow bathymetry of the Chukchi Plateau that really restrict the westward expansion of the gyre and result in strong asymmetry and potential implication for the gyre dynamics. So that was kind of the first step, and then we look at different model simulation and so on to understand what was going on 3D. But this data set and this analysis was really the beginning of everything. It gave us a lot of feature to, we describe a lot of feature then when we try, that we then try to understand with more modeling exercise, but clearly starting from observation is definitely the way to do it, in my view. And I will stop there. Thank you.
Thank you very much. Thank you very much, Camille. I think you've illustrated really well why we need more oceanographers to come to our satellite conferences to help us make sense of what we see in the data. So very, very well done. I see there is one question by Jérôme Bouffard, who's asking, is there any direct connection between freshwater content in the Beaufort Gyre and the interannual variations of deep water convection in the Labrador Sea? And if so, do you think they can be observed from surface altimetry-based DOT?
I think okay. In my knowledge, there are some, you definitely get a proxy for your freshwater content in the Beaufort Gyre from SSH or DOT. For sure, you can quantify that and the internal variability. The convection, in some cases, you can get an indication for a year with deeper convection based on DOT, but it depends a lot on the stratification and the local condition and so on. It seems to work fairly well in the Mediterranean Sea. It's more difficult in the Labrador Sea. There are a few papers out that try to investigate that. But you could try to build a proxy based on SSH of convection in the Labrador Sea. And then the link between the two, the problem is it's not just at the rate we accumulate fresh water and we release fresh water at the moment, that is not the full story yet. That's what I started my talk by showing a very extreme case based on CMIP type and projection over the next century, because you got very strong changes. I think at the moment, if you look at the data in the past 20 years, the story is more complicated and it's difficult to get a clear picture and making clear connection, because for sure there are other factors that are playing a role in what's going on in the Labrador Sea.
Thank you very much.
One could try. That's what I should.
That's right. That's right. It's worth a study, Jérôme, I reckon. Thank you very much, Camille. And that concludes this session on ocean and marine gravity. So please let me congratulate and thank all the speakers in this session and indeed the previous session for giving such a wonderful array of what we can do with an ice mission over oceans. So I think, again, the camels have made their case very strongly, I think. Thank you very much.
Thanks all camels. Great talk.
At which point I hand over to Tommaso. Are you still around to tell us, is it tea break, coffee break?
It is indeed, Christine, it's coffee break.
Okay. Over to you then.
We start at, what time do we start?
At 4 o'clock.
It's 4 o'clock. Yes,
yep.
Indeed.
Very good. Thank you. See you later.